In this lecture, we'll be looking at ARMA processes, specifically forecasting ARMA processes. So we'll look at examples of the AR1, the MA1, and the ARMA 1.1. So first, recall the definition of the AR or autoregressive 1 process. So we say that if you're given time series of these epsilon terms that are white noise process, mean zero, variance sigma epsilon squared, we say that the time series y1, y2, y3 is an AR1 process if, for constant parameters mu and phi, we have the following equation. And so remember, the idea here is that mu is the mean, phi is the memory, and our process is stationary if phi in absolute value is less than 1. And we think intuitively of this as the way yt differs from its mean comes from a piece, a memory piece, of how it differed from its mean at the previous time step plus a new noise term. The new noise term models new random information. And now we're going to sync this to a time series. So suppose we have time series data, y1, y2 up to yn. So here's our data here. And we have estimates of the parameters for the model. So we have an estimate phi hat, and let's assume that it is in size, in absolute value, smaller than 1. So we have a stationary time series model, and we have an estimate mu hat for mu. In that case, our AR1 model looks like this, where we reindex in terms of n. And our idea here is to forecast. What is our predicted value for the next value in the time series? So yn plus 1. And you can think of this as the time series data has given us our estimates, phi hat and mu hat, and now we're using that to say something about the next value. Well, when we look at our AR1 model here, we note first that we have our estimate for phi, and we also have our estimate for mu. Y sub n, this comes from the data. That is the last point in our given data set. And epsilon n plus 1, that is a future noise value. And since that's coming from the future, we can take its expectation, and we know that this white noise process is mean 0. So it has an expected value of 0. Putting this all together, we have that our predicted value, so our yn plus 1 hat, is equal to, so this mu we'll replace with mu hat and bring it to the right. So we have mu hat plus, we replace phi with its estimate, phi hat. We have yn, again, which is a data point, minus mu hat. And then again, we use that the expectation of epsilon n plus 1 is 0. And this gives us our predicted value, y hat n plus 1, which we write here. Now, if we want to predict 2 steps into the future, let's use this and note that if we have y hat n plus 2, this is going to be equal to, we can use this and increase the values of the subscripts. So on the left, we have y hat n plus 2, and on the right, we have mu hat plus phi hat times y n plus 1 minus mu hat. But note that this is a little troublesome, because yn plus 1, we don't have this as a data point. But we do have the predicted value that we just used or derived here. And so we can replace that yn plus 1 with this forecasted value. And so we get mu hat plus phi hat times, and now we can add that in here as mu hat plus phi hat times the quantity yn minus mu hat. So this expression here is that yn plus 1 hat. And we still have that minus mu hat. So all we did here was take this right hand of equation 3 and plug it in for this yn plus 1. So we replaced this yn plus 1 with yn plus 1 hat. And note that this then simplifies so the mu hats cancel, and the result is you get mu hat plus, notice you have a phi hat times a phi hat. So you have phi hat squared times the quantity yn minus mu hat. And so to predict 2 steps into the future, we can think of it as your estimate of the mean plus the memory parameter squared of how the process deviated from its mean at time n. And you can keep on going with this. So it shouldn't come as a big surprise that if you did this for 3 steps ahead, this same procedure would result in a phi hat cubed. And this is also a natural way to think of how the AR1 process works. Because if you're predicting out, say, k days in the future, then you have the mean plus the memory of k days in the past of your last deviation from the mean in your data set. And so this is our prediction k time steps out from time n. So if we're predicting for time n plus k, and again, the key thing to remember is that you don't have data for time n plus 1 or n plus 2 or n plus 3. The most recent data you have is at time n. And so this is your most recent data, and it was k time periods ago. So your memory parameter is raised, your estimate of the memory parameter is raised to the k, and that's what's added to your mean. It also helps to recognize that this, of course, is a stationary time series. And think about going a large number of time periods into the future. So think about k getting big. If k is getting big, we know our estimate we assumed was less than 1 in size. That means if we start raising that phi hat to integer powers k, phi hat to the k is getting smaller and smaller. So think of like phi hat being, say, 1/2. 1/2 squared is a 4th. 1/2 cubed is an 1/8. 1/2 to the 4th is a 16th. The higher that exponent k, the smaller phi hat to the k gets. And so phi hat to the k is approaching 0, which means this term here is approaching 0. And if that's approaching 0, as k goes to infinity, this predicted value, y hat n plus k, is approaching mu k. And, sorry, mu hat. And mu hat is nothing more than the mean of the process. So if you're predicting way out into the future, the further out you go, the closer and closer your prediction is to just your prediction of your estimate of the mean. So this is how we can use our AR1 process for forecasting. Let's take a look at the MA1, or the moving average 1 process. So recall the definition, same kind of white noise process. We say Y1, Y2, so on is an MA1, or a moving average 1 process, if for some constant parameters mu and theta, we have this equation here. And so in this case, the way yt differs from its mean is it has a little piece, it has a memory piece from the previous noise term, and then it has a new random noise term. And we don't have the requirements on requirements on theta for stationarity. This is always going to be stationary. And again, we want to sync this up to time series data, y1 to yn. Well, if we do that, we'll have estimates of our theta parameter, so theta hat, of our mean, mu hat. And then we have residuals, so we have estimates of the white noise terms, epsilon 1 up to epsilon n. In such a case, when we want to look at what's happening at time n plus 1, so the next time step, our forecast, yn plus 1 hat, we want to think about the information that we have here. Well, again, we have an estimate, theta hat for theta. We have an estimate, mu hat for mu. We also have an estimate of epsilon n hat for epsilon n. So we have a residual estimate. And as in the previous case, this is a future noise term, and we can use the expectation of epsilon n plus 1 being 0 as our best predictor of it. Putting this all together means that our forecast of yn plus 1, so yn plus 1 hat, would be replace mu with its estimate mu hat, replace theta with its estimate theta hat, and replace epsilon n with that residual epsilon n hat. And this is our prediction for time n plus 1. Which makes sense. The whole idea of the moving average model is that that next step has it's the mean, and then you have this memory parameter on the previous noise term. And we have an estimate on the previous noise term, that nth residual. Things change if you look more than one step into the future. And so this is our definition of our MA1 with the subscripts increased by 1. So we think about 2 steps into the future. And yes, we still have our estimate mu hat. We have our estimate theta hat. But the issue now is that both of these noise terms are future terms. We don't have estimates for them. We don't have residuals for them. We have residuals for time 1 up to time n, but we don't have residuals of these. And so they both, being noise terms, white noise terms, have that same 0 expectation, and that will be our best predictor of them. So for 2 steps in the future, our forecasted value will just be mu hat. And so we have that here. And this makes sense intuitively because the MA process remembers the noise term from the previous step. But we have no estimate of a noise term for the n plus 1 step. So without that, your best prediction is just the mean. And this holds true if you look further into the future. So if we look at yn plus 3, your epsilon n plus 2 and epsilon n plus 3 are again future white noise terms. And so we have the same approach where your predictor of them is 0, their mean. And so we have mu hat being the estimate of yn plus k for k greater than or equal to 2. And you can also see the autocorrelation structure of the MA1. Remember that it drops off to 0 after lag 1. And so you see that reflected here. Let's now combine these. So let's look at our ARMA 1.1 process. So recall the definition. We have the same kind of white noise process, and we say y1, y2, y3, and so on is an ARMA 1-1, or an autoregressive moving average process, 1-1, if for some constant parameters mu, phi, and theta, we have the following equation, and we see that this is nothing more than a combination of the AR1 and the MA1 process. So yt differs from its mean with this memory piece for how it differed from its mean in the previous time step, and then it has a memory piece for the previous noise term, and then a new noise term. As in the previous examples, suppose we have our time series data y1 to yn, and we want to use this for forecasting. So we have our time series data, we have our estimates as before. So we have an estimate phi hat for the memory parameter that's smaller than 1 in absolute value, so that we have a stationary time series model, estimates theta hat and mu hat, and then we have our residuals, so our estimates of the white noise terms. In this case, our ARMA 1-1 model looks like this, and we want to use this to predict what's going to happen at time n+1. So our forecast yn+1 hat. And as before, we have estimates. So we have an estimate for mu hat. We have an estimate theta hat. And we have an estimate of phi hat. So we have all these different estimates for the parameters. And then we also have an estimate for epsilon n, that nth white noise term. It's estimated by that residual, epsilon n hat. And then finally, our epsilon n+1 is a future term, so we do not have an estimate of that, but we know the best predictor of that is its expectation, which is 0. When we put this all together, and we replace each term in here by its estimator, we have mu hat plus phi hat times yn minus mu hat minus theta hat epsilon n hat, which is what we have written here in equation 12. And so now we see that our ARMA 1-1 model, so if we want to estimate the value one time step in the future beyond the time steps in our data set, then we have our estimate of the mean, our estimate of the memory parameter, times our estimate of how it differed from its mean at time n, how y differed from its mean at time n, minus our estimate of the theta parameter, so the noise memory parameter for yesterday's noise term, which we have an estimate of. So again, when you implement this, using information that we covered in the previous lectures, you have these values to estimate the parameters, and then you use your data, yn, here, to get that prediction for yn+1. If you want to go further out in the future, so say at time n+2, similar reasoning to what we went through before, when we looked at the AR process, well, we have mu hat to estimate mu. We have phi hat to estimate phi. But of course, yn+1, we can plug in our estimate, our prediction, yn+1 hat. For the noise terms, again, these are both future terms. So we don't have estimates of these. The best we can do is use the fact that both epsilon n+1 and epsilon n+2 have a mean of 0, and we use that as a predictor. We can now bring all this together to get our forecast for y at time n plus 2. So y hat at time n plus 2 is mu hat plus phi hat, and now we have our expression for y n plus 1 hat that we got on the previous slide, minus mu hat, which we'll write in just a second here. And then we know our best predictor for these terms is 0. So we'll have a minus 0 plus 0. And again, we can plug in what we had from the previous slide. So we have our y n plus 1 hat is mu hat plus this piece from yesterday, from the previous term, plus minus this piece from the previous noise term. So we have mu hat plus phi hat times yn minus mu hat minus theta hat epsilon n hat. And again, we see these mu hats will cancel. And as a result, we'll write it here. Our yn plus 2 will be mu hat plus, and you see you have a phi hat squared here, times yn minus mu hat, and here you get a cross term where you get phi hat times negative theta hat epsilon n hat. And so you see this is a little bit different than what we had for the AR1, because you do have this piece, this memory piece from 2 days ago, but now you get this cross term that happens because you have both the AR and the MA piece. When we want to forecast more steps ahead, say 3 steps or 4 steps, then the natural way to think of this is to come to this equation here and recognize that our future noise terms, again, have the best predictor of their expectation 0, and we just plug in the previous predicted value, the previous forecasted value. So our yn plus k hat will be mu hat plus phi hat times our yn plus k minus 1 hat minus mu hat. And so it's very important to note that this is a hat here, because this cross term between the phi parameter and the theta parameter will have an effect on this predicted value. But it's just a little bit easier to think of it this way. So if you wanted, say, k equals 3, the third predicted value, the third forecasted value, yn plus 3 hat, then you would plug in your yn plus 2 hat here that you just calculated. And that allows you to forecast into the future. And so these show you some basic examples, the most basic examples for the ARMA models. You can think of it as we have looked at the ARMA. Here we looked at ARMA 1.1, but we also looked at the ARMA 0.1 and the ARMA 1.0, which of course correspond to the MA1 and the AR1 processes. And you can do this for an ARMA 1.2, 2.2, just in general ARMA PQ, but the idea is the same. You look at your defining equation, you start projecting, forecasting 1, 2, 3 steps in the future, and for each equation, think about what you have estimates of and what you don't. And that allows you to use these to forecast, which is one of the reasons why you may use a time series model anyway, because you may want to make a guess at what your time series is expected to be in the future. And this gives you the way to do that.